which case the rotation of both the source and detector together, we eliminated translation completely. Can I eliminate rotation? That is the next logical big step that you can think about. Well, if I have to rotate eliminate the complete rotation, the first ecosystem is I know how to make the detector. The problem with this is the source is X-ray tube that we have been using for decades now, right? I mean when this is all developing. So, the detector technology is advancing. So, now I could just get an array of detectors. Not only that, because of that I could also get circular. So, I would first take arrest, not moving both, rotating both the source and the detector. I will have a stationary detector that is all surrounded the patient. So, here what is going to happen? I have completely done away with rotating. First, translating motion was avoided. Now, even the rotation of the detector is avoided. So, instead of doing that, what is done? Only the source is now moved, right, circled around the patient, and you have your detectors all around the patient. So, wherever the source is coming, that fan beam, the wide fan beam that is coming, only that part I can record, right. You could clearly see the advantage. It started giving exceptional, right, compared to where you started with 6 minutes or 5 minutes kind of acquisition time. Quickly you see when you come to the fourth generation, now you are talking about few seconds. Okay. So, this is very powerful. So, lot of applications started popping up from a clinical perspective, because these tools, these scanners were getting to a speed where it was meaningful that they could record some aspects physiologically, right. So, you want to do heartbeat. So, you want to be, I said the respiration can be held, but then you have some other moving parts as well. So, I want to do some remember the contrast agent. So, you want it to go, your blood vessel is moving, your heart is pumping. So, now if you get it to seconds, right, you have significant advantage. Okay, you can start to see things, applications that you never imagined before. So, it became very powerful. But is there any I mean like how we did for the other generations, what is it that we are going to pay up for? Of course, the cost and all is going to go up, right. Do not worry about the cost per se, but yeah, it is important, but technically what is happening? Technically you have gained in time. Is there anything else you are losing? Yes, two things. You had worried about scattering in the second generation and third generation because you had to have collimation. Here you notice, because the source is moving, you can have any angle, right. You cannot really have a detector with a fixed angle. When the detector and the source were moving together, you could have collimator based on the line of sight, right, from the source to detector you could have a collimator. Whereas here I can change my step size for my rotation of my X-ray tube source. So, in which case I cannot really have the same line of sight. So, a detector must be able to pick depending on where the source is shooting. So, you cannot really have a fixed collimator. So, the collimator aspect is done away with. So, the moment you do away with the collimator, what is the problem? A problem is now you are having multiple lines and you do not have collimation. So, even though you gain significantly with respect to time of acquisition, your Compton scattering is going to be a huge role. The only advantage, I mean, where do you gain? Oh, because I am going to have this surrounding in a circumference, the detector size can be bigger. So, if you have more area to pick the photon, probably your signal is also going up. So, your detector efficiency is increased, but then Compton scattering is going to be there. So, everything said and done, in fourth generation you are still able to get image quality comparable to your previous generation, right, with not so much significant improvement or significant increase in exposure, but very significant decrease in acquisition time. So these are very popular generations because you see you do not really lose much. CT itself you are seeing new aspects inside the body. So you see new information at if you accepted the initial quality when you got trained in this modality as a doctor, right? You are still seeing that quality, but now your clinical applications open because you can do it fast. Okay, you can start to see some anatomy which are moving, which is a huge deal, right? So these are, now the question is, good, where is my next promotion, right? What do I do? How do I push the market? How do I help the physicians more and come up with the next generation? Well, you look at it, the only thing that we have not touched so far in this paradigm is why is the source moving? Only one X-ray tube is there in all the generations. We saw only one X-ray tube is there, and the X-ray tube is moving. The challenge is, unlike detector like I said, we'll talk about it, but the advancement started to happen, and so they were, but X-ray tube has been there from from before. Even for projection radiography you use the same X-ray tube. So this is the active part, right? So it is heating, it is bulky, you have high voltage, so this is cumbersome. So you cannot have multiple X-ray tubes and try to rotate them. So it becomes challenge. So in some sense they didn't work on the X-ray tube aspect to have multiple source because of the bulkiness of the X-ray tube, and it's a very critical component. Unlike the detector, which the evolution was parallelly happening because of advancement in semiconductor, whereas this one is still was a challenge. So the next best thing would be, oh, I'll go to my physics. What is the role of a X-ray tube? Generates X-ray. How is it generated? Oh, I have a particulate, right, electron beam. That electron beam goes, hits the anode, out comes the X-ray, then you do filtering, shaping, all that. We know that. So now you are saying, asking the project manager, look, until now we have been doing, the only problem I see is the source. Instead of rotating the source, right, and you are saying rotating the source is challenging because it is bulky, all those things. So you cannot have even multiple source because it's wear and tear. Instead, how about if I can use the electron, right? I can move the electron around, that is easy. So instead of having X-ray tube moving around, I have come with a generation, right, which is called as electron beam CT. So instead of moving the X-ray tube, what can I do? I can move around the electron and have my anodes at different locations. So somehow if I can steer the charged electron, the kinetic energy, it will come and hit the anode and I can have X-ray generated. So you see this sophisticated instrumentation setup. So it is extremely complicated. But the idea is, instead of rotating the X-ray tube, the source, instead of doing that, I will create my X-rays from different viewpoints by keeping anode at those locations and steering my electron beam to that anode. How neat, right? I mean, at least from a scientist's point of view, from an engineering point of view, it looks cool, right? Look at the thinking. Instead of just moving the thing, you say, oh, don't do that. X-ray tube manufacturing ecosystem is set. We have vendor, so don't do that. Now you tell, okay, instead of doing that, can I just have fixed anode plates at different locations, right? The patient will not know anything. Behind, I will essentially have a big setup where I will have my electrons move around and go hit a particular anode where I want the X-ray view, right? So that is what this one is. So you had stationary source and stationary detector. Look at the advantage used for fast. We call this as cine loop, like cinema, right? Cine loop means you can actually get a movie. That is what it means. Used for fast whole heart imaging. So I could really get the whole heart pumping, I could get the slice of that, right? Whole heart imaging I could get. That is cool, right? Instead of just a bone fracture, maybe some abdomen is there as lump that is formed inside the body, which is all important. But then look at this cardiovascular, I can get my heart which is moving dynamics, I could get it because of the speed, fast acquisition times. So the idea here is you steer the electron rather than moving the exterior tube. Fantastic. You can see, very nice, had its role, it has its importance, but then always the engineering mindset and the application, there are two things, right? So the doctors, they started seeing things, newer applications started popping up. So it had it really served a purpose, but then the reach, right, it was very cumbersome, because look at the sophisticated instruments, the maintenance, all that was an issue. But it was nice generation, but it was not probably as popular as the. So if I didn't really have a need, I wouldn't go for this, right? So if I want to do heart imaging, yeah, I will try to use it, but otherwise I will not. I need a dedicated system setup where I know these patients are going to come and it is worth investing in this infrastructure. Only then I would go for this, right? So then what do you say? Okay, that is fine, but the part in me says, how do I maximize the benefit of these advancements so that more people can come, more affordable? What will I do? Right? I mean, that's the logic, right? What will you do? Well, I will go back to my drawing room and say, look, drawing table and say, look, your detector technology is evolving, right? Now, this is all fine. Where could I see the next advancement? I will say, you are now talking about only one slice, right? You are talking about only one slice. Go back to our projection radiography, we saw the whole chest region, chest radiography. So now I want to get greedy, I got the timing information, I got new applications. So can I now, instead of getting one slice, can I get more slice, so that I can do a volume imaging? I could have several slices put next to each other, actually I can do the whole volume. So I can go from my head to toe, right, in slice, so that I can have full 3D instead of just one slice, right? So, so that is the idea, right? That is the idea. So I want to get multiple slices, right? Good. The natural extension for that is, just to hypothetically think, if I want multiple slices, can I have detectors, like I can have line detectors you saw. So can I have detectors now in several detector lines covering an area? Not so fast, right? It was still evolving, but that would be prohibitively expensive. Then they looked at and said, look, what I want, I can do this slice, right? Instead of moving, so when we started, we were translating from left to right and then rotating the whole setup. Now I got one slice. So if I want to go from head to toe, what will I do? Oh, you could either move, right, move the slice acquisition like this, or instead of moving the instrument, you can have the patient bed, right, where you are lying. So I can motorize that, I can make it sophisticated, so that the acquisition is still whatever the previous generation, but I can move the patient so that I can go head first like this, right. So that is what is shown here. So why it derives its name as helical is, imagine you are moving in this direction and it is scanning in the rotation, right. It is scanning around the patient and the patient is moving. So what will it look like? It will look like a helix, right. That is why the name is helical scanner. So the biggest, this is not, this is in the 90s. So look at the progress from the 70s, right, when the initial work was done and they got the Nobel Prize for that. 70s, 80s, in the 90s you are talking about 6th generation. So every few years you are really pushing it. Okay. So here the point is everything else is similar, but you have added this bench. Your patient bench also is part of your instrumentation for data acquisition. It is not just patient lying. That is also technically contributing to the registration, because its position has to be recorded so that in the recon you know how it is happening. So in some sense technically it's a part of instrumentation. Okay. What are the other advantages that other technical advances that apart from that, the detectors that I talked about, what are the other advancements? See, you have now too many wires, right? So many detectors, each one is feeding out, right? You are reading the data out. Now you have the whole thing has to, the source has to move inside, right? Now you are saying the patient has to move, the bed has to move in and out. So you are talking about a lot of wires, rotation, translation. You don't want them to, get clogged or anything. So what happened is you had slip ring technology that was maturing, right? So without, so you could rotate this gantry, you could do all this without the wires getting intertwined. So the slip ring technology started to become really useful. They adapted that to this instrumentation. So the mechanical design and the electrical design for the control of both. You have two aspects, right? One is your data coming out. The other is all these control signals to move your translate, rotate your bed or your source, that those wires. So they were able to essentially use slip ring technology, became very popular and very useful, and therefore you could start to do all the integrate patient bench motion and other things without much trouble. So helical scanner, so you could get entire abdomen or chest completed in 30 seconds. Fantastic, right? We talked about, say, in second generation we were talking about some 30 seconds. Now, but that was one slice. Now you can get a whole chest or whole abdomen. So you are talking about, say, for example, several centimeters, right? Whole chest, whole abdomen. You are talking about several centimeters. You could get in 30 seconds, right? Fantastic. Well, so far so good. So this is popular as well, but then I would still like to have multiple slices. Can I do even faster? How can I do even faster? Well, I can do even faster. The same logic, instead of moving the patient, right, translating the patient, can I go back to your first generation? You are doing translation. We wanted to avoid this translation to gain time. Now you are moving the patient in helical. So you are getting 3D, you can get the whole different slices. But if I want to reduce the time even further, what will I do? Or instead of moving the patient, can I have multiple detectors, right? One row of detectors you saw. Can I have another row of detectors, right? So if I have two rows of detectors, I have two slices recorded at the same time. If I have three rows, I get three rows of slices recorded at a time, right? So again, so the logic was in the 7th generation, right? You got what is called as multiple detector array. So when you have, when they say array means you have several elements, array of elements. Now you have multiple detector arrays. So you are single, right? This is the fan beam. You have one full array. This was the thing in the 4th generation, right? 3rd generation, 4th generation. 4th generation essentially you were rotating and getting it. So 3rd generation, for example, you got one array. Now what you are doing is you can get multiple arrays, you can position. Only thing is what you have to do, instead of sending a fan, right, with only thickness proportional to one detector size, remember how the X-ray tube generates. It generates a cone, right? Its point source, it goes like a cone. That's how we did in projection radiography, right? So here deliberately I have to make sure that I have this fan but the fan should be spreading over how many ever detector array I have. If width of height of one detector is x and I have 4 arrays here, then I have 4x. So I have to know my width has to be 4x. Okay. So the idea here is direct brute force extension of the previous generations with advancement in the array. So you can have multiple detector array. So there is a site which I accessed a year ago. I found it to be very useful. There are several more animations and sketches that I found to be useful, right, along with in the line of what we are discussing here. Okay. I have no conflict of interest. Okay, so it's just I found it useful, so maybe you may want to take a look at it. So that is your 7th generation. So good. Do you think is there anything else that we could do? Right, it is 2000s. Anything else we could do? Right. Well, not. I mean, still you can do. You can. What we are silent so far, right? What happens after 2000? Did nothing happen? Right? What has been happening in the last decade or two? Everything done? Not really. I mean, these were developed in the 2000s and now it's becoming popular. So you would hear multi-size scanners, right? Typically 64 slice scanners that are coming to the market. If you are in, say, India, for example, these are still niche instruments that are there only in few select hospitals, right? So it is still becoming popular, right? So we are in that stage, but where is the lot of developments happening? We'll come to it. The all until now we are talked about only data acquisition, hardware and instrumentation. We have not really talked about the computation aspect of it, right? After you get the data, we have to recon, get the images of the slice. Now you are getting so many different slice volumes, so you have so much data. So lot of effort still is going on. How do you digest this information, right? How do you visualize this information? 3D, 4D, how do I plot it? How do I see what is happening in certain applications, right? So I send contrast agent and I see the heart pumping. So I have several aspects that I want to visualize. How does this perfuse into the tissue? So you have higher orders. So you have so much data, so much new information coming, and you have to churn all this to do the computation. And no guess here, at this year 2021, you would have probably lot of buzzword you would see is all about big data, deep learning, AI, right? So you have a lot of data coming in. So a lot of research in the last couple of decades has been essentially going towards how do we handle so much data? Can it be patient specific? How do we handle the data, visualize the data, process the data? So the second part of this module, right, to do with the image recon, that will be very interesting in that sense. Now we have just covered the data acquisition generations. How has it come along? Okay. So that said, essentially the idea is reduced scan time and increased Z resolution. Z is, remember, XY we used for the plane of the image. So if that's what we are going to, so the other direction was Z in our projection radiography coordinates. If you look at it, we will redefine the coordinate one more time when we actually do the recon, because you need to know where is the signal coming from. But generally, if you vaguely remember how we did projection radiography, we always use f of x comma y as the input source, 3D object, right, image of the 3D object, the g of x comma y on the and the z we used it for separation between the source and detector, right. So z is your thickness. In this regard, it's the thickness. Okay. So we can get reduced scan time and increased. If you have multiple detectors, I could get slice thickness can be improved, because that will be about the size of the detector, right. So you can get 64 slice per rotation. Look at this, whole body in about 30 seconds, right. So powerful. These are the different geometries that we have talked so far. Source, right, you get this line, first generation. Then we talked about fan beam. This is called as your cone beam when you did the 2D, right. You had your detector array stacked, volumetric, okay. So this is your cone beam. So now the question is, we got the data in this format. Along the line I get one value, along the line I get another value. So I have collapsed, I have projected this. This is the data I have. Like this I have it at different angles. This is along this line I have a value, along this line I have a value. So, but it is arranged in a curvilinear fashion, and I have it for different rotations. So these are the raw data that you have measured using the different schemes, different generation detectors that we have talked about. Of course, we will right now the current generation you are talking about multiple detectors. So it is an area. So you have one detector, next detector line, third array, fourth array. So you have several of them. Clear? So this is about your data acquisition part of your instrumentation. Major development of the different generations. The different components in this thing, several of this we saw. X-ray tube, for example, is X-ray tube. There is nothing new to cover. So we have X-ray tube already. What we need to still cover is some specifics that are there, but major components in the X-ray projection system that we covered will be used here as is. The major component that is slightly different is your detector part. So most scanners use only X-ray tube, right. That is why. So this is nothing different from what we have covered already because of this reason, okay. So again, improvisations, we could use multiple energy sources, right. So I could excite with 80 kilovolt peak, I could excite with the next 140 kilovolt peak. I could record the data at two different energy levels. That is where you talk about. So you recall the basic plot that we had, the hill type kind of energy versus X-ray intensity, right, when we talked about Brahmstrahlung. So that is the spectra that goes in, right. So you could do that at two different energy levels, because we know your mu is a function of energy also, right, material property. So you kind of do the data acquisition at two different energy levels, then we could also use that information to tease out the difference in the material property. So dual energy X-ray you could do collimation and filtering are slightly different. You still have, we saw some of the collimation. Why is it slightly different? Because in projection radiography we basically sent a cone, right. Here we talked about pencil beam or fan beam. Even if it is a cone, it is not cone. No, your cone as in you don't have a curvature. You don't want that. What you are wanting is the slices. So it is like this. The thickness direction is like this. So if it was a cone, it would be like this, right? But you are talking about parallel, but it will be fan in the direction. In one direction it will be a fan, the other direction it will be, so it is not technically a cone, but it is. So you have to make special filter, you remember about the collimators, how we did. You have to shape it, have a slit, so that I can increase the, if I am doing only one detector array, I would want the cone that is coming out, I want two leads, so that only along that plane, right, along that slice X-ray goes. If I want the slice to be thick, I will make this. So the filtration, that is your, your field of view could be adjusted. When we talked about filtering, we talked about filtering in the context of removing the low energy, right. So here deliberately what you do is you make it hard. Okay, what do you mean by hard? Hardening the beam. Beam hardening, what does it mean? We covered this. You remove the low energy so that you are moving it to the right. Okay. So fan beam angle of 30 to 60 degree is used with fan thickness. The fan thickness is the thickness direction, right, slice thickness direction. So you are typically in the order of 1 to 10 millimeters. So here most filtering, it's very similar, but it's a little more aggressive here. So you get more hardened beam. So the concept of filtering, all those things are very similar to what we did in projection radiography. But here we are making it more hard. Why? When you mean making it more hard, what is happening? You are narrowing the spectrum and moving it, right? You are narrowing the spectrum. Initially it was wide. You preferentially take the lower. So the width of the spectra is reducing. It becoming narrow. That means you have only less number of energy distribution. You don't have wide range of energies. Why is this important here? Why am I aggressive? I want to really reduce it. Oh, in projection radiography, right? In projection radiography, even though we wrote the equation, we said monoenergetic, polyenergetic, even though we recognized it as polyenergetic, we were okay with not being aggressive. Why? Because image was formed, right? Image was formed, and average energy equivalent to interpret was good enough, because anyway I am collapsing the whole dimension. So that was good enough. Whereas here, the data that you are recording, you have to now start to reconstruct at different locations. So that means my assumptions, right, I am going to start with a value that is detected, I have to have a model, I have to reconstruct. So that has to be the model, right, the image, the attenuation law, the model that we made for the signal, that has to be, we have to practice, be as close as possible to the model that we described. And that happens if you have monoenergetic case, it is easier to handle. So as far as possible you make it hardened, so that even though you know it is polyenergetic, your estimate of an equivalent monoenergetic can be used in the recon, right, mathematics, and you won't be too far away from the reality. Okay, so that is the, because ideally, ideally you might say I want only one energy, but that's not going to happen. So you can be as narrow as possible. Okay, so source is more monoenergetic. It is not monoenergetic. It is more monoenergetic than before. That's why you want to harden it. Okay, so this is one thing that is specific to CT, because you are going to start with the detected value and do reconstruction. Okay. Good. So much for X-ray source and collimation. We talked about that. What are the other aspects? The most important aspect, I did say that. Oh, advancement in detector, right? That's what we were exploiting. But you really think about it, the major difference between your projection radiography, right? What was the bottleneck of projection radiography, and it took so much time. It's not that people were not aware of the mathematics. In fact, you will be, I was really, it was a moment to really appreciate these things. I learned that the radon, the work by radon, right, radon transform, which we will be heavily using in the recon, right. Those, lot of those theorems and work happened, radon published in the early 20th century, 1915, 16. So that is kind of contemporary, right, about 10 years after your X-ray started coming for medical applications, medical imaging application. So in some sense, the mathematics he was dabbling with, how to reduce the dimensionality and recover the dimensionality from a mathematics perspective. So he has done a lot of radon theorem and other things happened those time. But when did your CT happen? And the problem of, oh, I am losing my depth, is known to the the physicists that time also. But and the doctors would probably also share that opinion. Oh, I want to see what is there inside, not just the projection. But the problem was they didn't really have that. They were using, so the parallelly the photography was also developing, right? Photographic, film chemistry, development chemistry, all that things were also rapidly progressing. Light was a big deal, right, in the early century last year, last century, early last century. So the point is the need was there, but the biggest bottleneck was how do I record the data, right? So the detection part, rest of it same, right? X-ray tube, the detector was the key. So now we wanted to have a detector where I could actually record the value and take it for computation. That is the key. So what happened? Your semiconductor, those started, your diodes, right, transistors, those started appearing. They became very mature, right. So advances in solid state electronics, essentially that translated to, so the idea of modern detectors, right, where you can do CT. So that transformation started post World War II perhaps, right, after you had semiconductor devices that were mature enough that they understood they could use for this. Then probably they worked for a decade or so to come up with this idea of, okay, I could use these detectors and collect the data, the first generation, right. So in some sense, even though you would say CT was introduced, the first shown to work in the 70s, but your X-ray projection radiography, X-ray was about 75, 80 years earlier than that. It is all because at that point of time, what are the other, so it's very interdisciplinary, right, multiple disciplines have to progress. So here big development came because of the development of the detector part of it, mostly due to your semiconductor electronics. So silicon, your scintillator crystal, right, you might look at what is it. So look at the objective of the projection radiography instrumentation on the detector side. What was it? Oh, X-ray photon came, it hit the photographic film, the conversion ratio was poor, and therefore they used some material, phosphor, active material, right. Phosphor was there. What was it doing? It was the intensifying screen. Go look at that. So it was trying to convert the X-ray energy to light energy, and that light photon went and spoiled the X-ray. Now what I want? Same thing, I cannot measure the X-rays. So here also I want to convert the X-rays. I want to convert the X-ray photons into visible light photons. But then I want to measure that photon, take it out, read that, so that I can do operations with it, right. So you started getting these photodiodes, right. So essentially this advancement led to the scintillating crystals, also like I said calcium tungstate, what we used, right, what Edison was using in the early developments. But once, so that was still used in the X-ray film, right. Whereas this detector, you started getting rare earth materials, okay. So you had all these which will use for scintillator. What is scintillator? It is converting your X-ray energy. So inside, so X-rays come and fall on the detector. And what does it do? The scintillating crystal essentially convert this X-ray into light photons. And once that happens, that feeds into your photodiode, and then I can record, right. I can get my voltage, I can record what is coming out each of the locations and do computation. So two major advancements. One is your detector part, advancement of this, and then having said that, computation, I am not going to cover about that, but the idea is once you get that, the generic advancement in computation started lending its way. So it's the CT detector. This is an important advancement that enabled the acquisition of data so that it can be done for reconstruction. Okay, so this is an important piece in the instrumentation. So you not only had like this, you had several other versions as well. For example, if you look at third generation, where you had collimator, that was direction was very important, it was aligned with the source, right. So in those cases we also talked about, because of that the signal detection goes down, because you have your collimator and it is in that, so your scattering was supposed to be avoided, but also because of neighboring beams and you put collimation, your efficiency also goes down. How do they, so essentially they also had few other ways, mostly for the third generation, which this was very directional detector, where you have a xenon gas tightly packed chamber. So the moment X-rays come and hit, you have ionization that is taking place, and then you had cathode that was at a very you had this cathode and anode, right. So you had a very high voltage differential that was kept. Therefore, when X-rays came, it ionized the xenon gas. When ionization happens, you have a voltage difference, you have current. So they could essentially use that conversion. So this was very useful for when they needed very directional amplification of the signal, mostly for the third generation. Okay. So towards the end, what happened? Oh, so this was there, line array was there. In the development of this basically led to, so in 3G systems require very small directional. So xenon gas based detector was used. But like we said, more advanced scanners nowadays, we are talking about not just one line, we are talking about arrays of this. I mean, array two dimensional, right. So you have one array next, so you see several of them, one row, next row. Okay. So in multiple detector array system, individual solid state detector, so you are now talking about 1 mm cross 1.5. 1 mm is in the if you want to call it along the width, right. Height is 1.25 mm, the slice thickness is in this range. So you still see it's fairly small. I mean 1 mm 10, right. So the crystal is only 1 mm in height. So you could get as thin a slice as 1.25 mm, which is pretty damn good, right. So the advancement is because of the advancement in the detector. So not a surprise, that is what we saw in our advantages, right. You have these cell phones having cameras now with so much pixels, right. All this advantage we get with CCDs, all that, this advantage is also translated. I mean, these are all happening parallelly, and also medical imaging CT detectors benefited out of those development, not just the photography part. Okay. Okay. So we are not going to really go in deep with the other instruments in the instrumentation. One is the gantry. So what is a gantry? You saw the big when you see the photo of a CT, right, you see this housing where the source detector ring is there and the source has to move, right. So the whole thing has to rotate. So that whole part, the mechanical casing, all that is called as your gantry. Okay. And so these are kind of very matured, and so we are not really going to go into deep in this gantry. Slip rings, like I said, so you have to have the gantry should rotate, for example, then you have your data channel signal coming. So slip rings, that is another part that is used. So this mostly the other parts are patient table. Mostly these parts are in some sense traditional mechanical design, electrical design, engineering, which was well matured. That was not the bottleneck, so it kind of came along with that. Okay. So there is not no real new sophistication that was required. This is a big deal. Why the generations changed and CT evolved? Your detector is a big deal. So detection and the strategy of acquiring the data, that is changed to address this big limitation of how do I get through the slice, right. That is changed, and then most important part, what do I do with this data? So now I acquire the data, what do I do with this data? I have to do the image formation. We do not call it, we will cover it in the title of image formation, but then here image is not formed by itself. You are actually doing reconstruction. You are forming the image by reconstructing. What do you mean by reconstructing? I get the data, right, using these strategies. I have to now reconstruct what would be along the path, right. So, with respect to instrumentation, I think we will stop here. Perhaps it will be a good point to stop now and start the imaging aspect, the image formation module in the subsequent lecture. Okay. Thank you.